Welcome viewers. Now we are going to discuss some applications of Ampere circuital law. Okay, the first simple application is B due to a thick wire. Okay, in all our previous discussions we have seen current carrying wires. All the current carrying wires are assumed to be thin. All the current carrying wires are assumed to be thin, but there is no rule that every current wire should be thin. What happens if the wire is thick? Okay, so whenever I say thick wire, okay, then the question comes, what is the field outside the wire, what is the field on the wire, what is the field inside the wire, like this. Okay, now B due to a thick wire, that's what we want. Consider a thick wire like this. Of course not this thick. We don't call a wire this thick as a wire, it becomes a rod. Okay, right? Just for explanation purposes we take like this. This is a wire of radius r. This is a wire of radius capital R. Okay, carrying a current, uniform current like this, carrying a current I like this. Okay, this is the axis of that wire. This is the axis of the wire. Now my aim is to find out the magnetic field at a point outside the wire, on the wire, inside the wire. Means the point P, suppose is here. It is at a distance small r from the axis of the wire. Now whenever the wire is thick, we should consider the distances from this axis. Okay, where small r is greater than capital R. This is first case. Okay, next one, field on the wire. Field on the wire means consider a point Q like this, okay, which is on the wire. What is the magnetic field on the surface of the wire? Here small r equal to capital R. Okay, next I'll consider some point Z inside the wire. Okay, what is the magnetic field at a point inside the wire? In this case small r is less than capital R. Means the three cases is small r greater than capital R, field outside the wire. Okay, small r equal to capital R, field on the wire. Okay, small r less than R, field inside the wire. Okay. Okay, now first case is what is the magnetic field at a point P which is a distance small r, where small r is greater than capital R. Okay, same now I'll consider an Amperean circular path. Amperean circular path will be a circle like this of radius small r around the wire. Okay, right, at every small element of length assumed to be in the direction of B. Okay, circular integral B bar dot dl bar. B bar dot dl bar is nothing but circular integral B dl cos theta. Okay, at every point on this Amperean path, B and dl are always in the same direction such that angle between them is 0. The cos 0 is equal to 1. So this simply becomes circular integral B dl. Okay, right, because every point on the circular path is the same distance from the axis. B is also same at every point on the path. B is a constant, bring it out, so B equal to B into circular integral dl bar. Okay, circular integral dl now what is circular integral dl? Is nothing but the circumference of this circular Amperean path, which is nothing but 2 pi into small r. 2 pi into small r, that is nothing but B into 2 pi r we get. Okay, so Ampere's law says as what? Equated to mu naught times the net current I enclosed by what? Net current I enclosed by this path. What is the net current I enclosed by this path? Net current I is nothing but current in the wire, I only. So it is simply mu naught I. Okay, therefore B at an outside point, B equal to mu naught I by 2 pi small r only. Okay, B at an outside point is mu naught I by 2 pi r, where r is the distance of that point from the axis of the wire. Okay, this is same as what we got due to a thin wire. The only difference between thin wire and thick wire is what? There is nothing like thin wire and thick wire actually. Okay, if the radius of the wire is capital R and the point P which I choose outside the wire, if it is very close to the wire, okay, such that the distance radius C is very large compared to the distance, it becomes a thick wire. Okay, if I choose a point at a very far off point where the distance of that point from the wire is suppose say 2 meters and the wire is only suppose say half centimeter thick or 5 mm thick. Okay, radius of the wire 2 mm is nothing compared to 2 meters. So a wire with what you call 2 mm radius, that is 4 mm thickness, also can be taken as thin wire only. Okay, or you take a very thin wire of radius only 1 mm. Okay, but you are choosing a point very close to the wire. Okay, the distance between the wire and the point is comparable to radius of the wire, then this thin wire also becomes a thick wire. Means whether small r is greater, very much greater than capital R, every wire is a thick wire. Sorry, everything is a thin wire. When small r is comparable to r, okay, it becomes a thick wire, that's all. Okay, so B due to thick wire or thin wire at all outside points is mu naught I by 2 pi r. The only difference is if it is a thick wire, you have to consider the distance from the axis. If it is a thin wire, you can neglect that radius part, extremely small, simply take from the surface only. Okay, next, what is B on the surface of the wire? On the surface of the wire also I will consider one Ampere path like this. Everything is same, B and dl will be in the same direction. Okay, cos theta equal to 1, so B dl, okay, B into, instead of what is the radius of the circular path, it will be 2 pi r. Means if I replace small r with capital R, okay, B equal to mu naught I by 2 pi capital R, where R is radius of the wire. This is the expression for B on the surface of the wire. Okay, B on the surface of any current wire is equal to mu naught I by 2 pi into the radius of the wire. Okay, now the interesting point is, what is the field inside the wire? We have to see. Okay, that's the last aspect. Okay, now now I want to find out the field at the point inside the wire. This is the third case. Okay, now consider a point P which is at a distance small r from the axis, where small r is less than capital R, that is the point is inside the wire. Okay, the entire wire is carrying a uniform current I. Now I'll define a quantity called current density J bar. J bar is nothing but, okay, current per unit cross-sectional area of the wire. What is cross-sectional area of the wire? Cross-sectional area of the wire. What is the area of this circular wire, cylindrical wire of radius r? Area, cross-sectional area is nothing but pi r square. Current per unit area will be equal to I by pi capital R square. Okay, direction of J bar is in the direction of current only. So J bar is equal to I by pi r square. Right? This is called current density, current per unit cross-sectional area of the wire. Means current density through the entire wire. Okay, it is like this, I by, right, pi capital R square. Now, what is the magnetic field at this point, small r, which is inside the wire? Here also, I'll consider a circular Ampere path like this. And again, I'll consider a small element of length dl. The dl is assumed to be in the direction of B only. So, both B bar and dl bar are in the same direction everywhere on this path. Okay, here also, dl bar is like this. B is also tangential. Angle between B and dl is theta equal to 0 degrees. Okay, so circular integral B bar dot dl bar equal to, right, circular integral B dl cos theta. Okay, angle between B and dl is 0 degrees, cos 0 is always 1. So this becomes simply circular integral B dl. Because every point on the circular path is the same distance from the axis of the wire. Okay, B will be same throughout the path. So B can be taken as a constant and brought out. Okay, circular integral dl. What is circular integral dl? The total length of the circular path inside the wire. Okay, that path has a radius small r, so the circumference is B into 2 pi r. Okay, right, now Ampere circuit law says what? This B into 2 pi r must be equal to mu naught times the net current I enclosed by the path. Here the difference comes. What is the net current I enclosed by the path? Net current I enclosed by the entire wire is I. But what is the current enclosed by this path only I want? Okay, so I'll call that as I dash. So it will be mu naught I dash, we can write. Now we have to find out what is that I dash, means how much current is passing only through this part of the wire only. Okay, current through this path only. Okay, how do we evaluate that? Current through the entire wire is I. Okay, current density means what? Current per unit cross-sectional area of the wire is I by pi r square. So what is the current through this, right, section under consideration? I dash equal to current per unit area into area of this path. Area of this path is pi small r square. What is J? J equal to I by pi capital R square into pi small r square. Pi and pi gets cancelled. So I dash equal to I small r square by capital R square we get. Now we have to substitute this I dash, means current passing, the effective current passing through this cross sectional area is I dash is nothing but I into small r square by capital R square. Now substitute that I dash there. B into 2 pi r equal to mu naught into, yeah, one more thing, that now in this case the mu is not outside the wire, not in air, it is inside the wire. So you can take that mu naught permeability as permeability of the wire. Okay, permeability of the wire mu into, right, I dash. I dash is nothing but I into small r square by capital R square. I into small r square by capital R square. Okay, this small r gets cancelled. So B equal to, okay, mu naught I by 2 pi capital R square into small r. The small r will remain here. Okay, so B due to a thick wire at any internal point inside the wire at a distance r from the axis can be written as B equal to mu naught I by 2 pi capital R square into small r. Okay, this is the expression, means B is not uniform. What is B on the axis of the wire? B on the axis of the wire means I have to take small r is equal to 0. Put small r equal to 0 on the axis of the wire, B equal to 0. Means due to any current wire, what is the magnetic field on the axis? At the axis, it is 0. From the axis, right, as you are going away from the axis, small r keeps on increasing. So B also keeps on increasing linearly like this. Means if you draw a graph of B versus R, okay, this is the point equal to the radius of the wire capital R. At a point inside, when small r is equal to 0, B is equal to 0. Okay, inside the wire as you are going away from the axis, B is increasing linearly like this. Okay, and becomes, what is B value on the surface of the wire? When you reach the surface, put small r equal to capital R. When you put small r equal to capital R, here r gets cancelled. B equal to mu naught I by 2 pi capital R. That's what we have got. Okay, in the earlier case also. So on the axis of the wire, B is the maximum, and outside the wire, B equal to, right, mu naught I by, right, 2 pi r, as R outside the wire keeps on increasing, B value keeps on decreasing, means variation of B will be like this. That is, B is proportional to R here, B is proportional to 1 by r outside the wire. B is maximum on the surface of the wire. So due to any current wire, okay, what is B value? B value is 0 on its axis. B value becomes maximum on the surface, and again at infinite distance, B is equal to 0. Okay, this is the application. So inside any wire, what is B value? B value equal to, now I'll take this I by pi r square as what you call current density. So it is, right, mu, that is the permeability of the material of that medium. Okay, right, mu by 2, right, I by pi r square is nothing but J into R. Okay, this is the magnitude of the magnetic field at a point inside the wire which is having a current density J. Mu by 2 into J into R. R is the distance, okay, from the axis of the wire. Okay, thank you.